Who is taller, a man 73 inches tall or a woman 68 inches tall? The obvious answer is that the man is taller. However, men are taller than women on the average. Suppose the question is asked this way: who is taller relative to their gender? A man 73 inches tall or a woman 68 inches tall? One way to answer this question is with a z-score. The z-score of an individual data value tells how many standard deviations that the value is from the population mean. For example, a value 1 standard deviation above the mean has a z-score of 1, and the value 2 standard deviations below the mean has a z-score of -2. Let x be the value from a population with a mean and standard deviation. The z-score is z equals x minus mu divided by sigma. So this is another important formula for you. You might want to make note of that on your formula sheet. As an example, a National Center for Health Statistics study states that the mean height for adult men in the United States is, mu is 69.4 inches with a standard deviation, sigma, of 3.1. The mean height for adult women is 63.8 inches and a standard deviation of 2.8. Who is taller relative to the gender? A man 73 inches tall or a woman 68 inches tall? From here we compute the z-score, x minus mu. So x is the 73 for the man. That's the data value. Mu is the mean that's given in the problem, so that was 69.4 up here. And 3.1 is the standard deviation. So you subtract 73 minus 69.4, press the equal button, and then divide by 3.1, and you get 1.16. Then you do the woman's height, 68 minus 63.8. So 68 is the data value that you're looking for. 63.8 is mu, and 2.8 is sigma. You subtract that, press equal, divide by 2.8, you get 1.5. The woman is taller relative to the population of women's heights. Her z-score is higher. If we look at the z-score with the empirical rule, you'll notice that it follows the same shape. Since the z-score is the number of standard deviations from the mean, we can easily interpret the z-score for bell-shaped populations using the empirical rule. When a population has a histogram that is approximately bell-shaped, then 68% of the data will be between z-scores -1 and 1. So that's from here to here, 1 standard deviation away. 95% between -2 and 2, so this is 2 standard deviations away. And again, 3 standard deviations away, -3 to 3, or almost all, or 99.7% of the data falls within 3 standard deviations. Quartiles. In the previous sections, we learned how to compute the mean and the median of data set as measures of center. Sometimes it is useful to compute measures of position other than the center to get a more detailed description of the distribution. Quartiles divide a data set into 4 approximately equal pieces. The first quartile is Q1, separates the lowest 25% of the data from the highest 75%. The second quartile, Q2, separates the lowest 50% of the data from the highest 50%. Q2 is also the median. Third quartile, Q3, separates the lowest 75% of the data from the highest 25%. There's several methods for computing quartiles, all of which give similar results. The following procedure is one fairly straightforward method. First, you need to arrange the data in increasing order. Very important, it has to be in increasing order. Let n be the number of values in the data set. So again, if you have 10 pieces of data, n would be a 10. To compute the second quartile, simply compute the median, which is the number in the middle, right? If you have an odd number, it's the number in the middle. If you have an even number, you take the 2 numbers in the middle, divide by 2. For the first or third quartiles, proceed as follows. For the first quartile, compute L, it's 0.25. Again, that's 25%, 0.25 times n. And the third quartile is 0.75 times n. This step 3 here is important. If L is a whole number, meaning after you do these multiplications here, if L is a whole number, the quartile is the average of the number in the position L plus the number in position L plus 1. So for instance, if you do this calculation and you get an 11, you're going to take the 11th position number and the 12th position number and divide it by 2. If L is not a whole number, round it up to the next higher whole number, and the quartile is the number in the position. Again, you're calculating positions, you're not calculating values corresponding to the rounded up number. As an example, they give some rainfall in Los Angeles during the month of February over several years. Compute the quartiles for the data. So the data are already in increasing order, and there are 45 pieces of information. So they just literally counted how many there are. For the first quartile, we compute 0.25 times 45. Again, there's 45 pieces of information. First quartile is 25%, so 0.25, and you get 11.25. Since this is not a whole number, you round it up to 12. So you're looking for the number in the 12th position. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is the 12th position right here, 0.83. So Q1 is 0.83. Then you get the median. Since there's 45 pieces of data, it's the number in the middle. This right here, 3.12, is the number in the middle, and that would be the second quartile, 3.12. Third quartile, 0.75 times 45. Again, 45 pieces of information. You get 33.75. This is not a whole number, so you round it up to 34. And you take the number in the 34th position, which is right here. It's 4.89. So the third quartile is 4.89. You can look through, if you have a TI 84+, you can look through some of the calculator methods to get this. Visualizing quartiles. Following is a dot plot of the Los Angeles rainfall data with the quartiles indicated. The quartiles divide the data set into 4 parts, approximately 25% of the data in each part. So a dot plot is basically just taking each information and making a dot for each value on a number line. If, for instance, I had 2 values that were 8, I would put 1 dot on 8 and then another dot on top of 8. But you can see you have the smallest data value, the first quartile, the median right here, third quartile, and the largest data value. We also have percentiles. Quartiles describe the shape of a distribution by dividing it into fourths. Sometimes it's useful to divide the data set into greater numbers of pieces to get a more detailed description of the distribution. Percentiles divide a data set into hundredths. For a number p between 1 and 99, the pth percentile separates the lowest p% of the data from the highest 100 minus p%. This is the method for computing percentiles. Arrange the data again in order. Let n be the number of values in the data set. For the pth percentile, compute L equals p over 100 times n. Again, we have, if L is a whole number, the pth percentile is the average of the number in the position of L and the number in the next position. If L is not a whole number, round it up to the next higher whole number. The pth percentile is the number in the position corresponding to the rounded up value. Again, we're getting numbers in positions. When you do the formula, you're not getting the number, it's a position you're calculating. So here we are again with the rainfall, and we want to know, compute the 60th percentile of the data. So the data is already in order, there's 45 values, and you want the 60th percentile. So you do 60, so that's the 60 goes on top, over 100 times 45 pieces of data. This time it came out to a whole number, 27. Those other two we did when we did quartiles, they were decimal numbers, so we had to round up. So now we're using the other method. 27 is a whole number. So what you want to do is look for the 27th position and the 28th position. So you count through it. This is the 27th position. This is the 28th position. You add them up, divide by 2. So the 60th percentile would be 3.575. And if they put it on the dot plot, it would be right there. Sometimes you are given a value from a data set and wish to compute a percentile corresponding to the value which means you want to go backwards. Like you want to know, well, this value, what is the percentile? Following is the procedure to do that. Arrange the data in order. Let x be the data value whose percentile is to be computed. Use the following formula to compute the percentile. So the percentile is equal to 100 times the number of values less than x plus 0.5 divided by the number of values in the data set. Round up to the nearest whole number. This is the percentile corresponding to x. So let's look at an example of how to do this. The question is, 1 year the rainfall was 1.9. What percentile does this correspond to? So that's right here. So now we want to know, well, what actual percentile is that? So the data is already arranged in order. There's still 45 numbers. There are 18 values less than 1.9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 numbers are less than 1.9. So we're gonna do 18. That's the numerator right here, less than the number we want to look at, plus a half, divide by the numbers in the data set, so that's 45 times 100, so 18 plus a half, so that's 18.5, divided by 45, multiply by 100, you get 41.1. We round the result to 41, and the value 1.9 corresponds to the 41st percentile. The 5-number summary of a data set consists of the median, the first quartile, the third quartile is the smallest value, the largest value. These numbers are generally arranged in order. So you have the minimum number, first quartile, median, third quartile, maximum. The following table presents again the rainfall. We did these values before. The first quartile was 0.83, the median was 3.12, the third quartile was 4.89. The minimum number, which is the smallest value, is 0. The maximum is 13.68. So the 5-number summary is given this way. Literally, you just write the numbers in order from minimum, quarter 1, middle, quarter 3, maximum. Here is some examples for the calculator if you want to go through those. An outlier is a value that is considerably larger or considerably smaller than most of the values in the data set. Some outliers result from errors. For example, a misplaced decimal point may cause a number to be much larger or smaller than other values in the data set. Some outliers are correct values and simply reflect the fact that the population contains some extreme values. As an example, the temperature in a downtown location is measured for 8 consecutive days during the summer. The readings are in Fahrenheit: 81.2, 85.6, 89.3, 91, 83, 8.45, 79.5, 87.8. And the question is, which reading is an outlier? Is the outlier an error or is it a possibly correct? So here you can clearly see 8.45 is the outlier. It's likely an error resulting from a missed decimal point. One method of detecting outliers involves a measure called interquartile range. So the interquartile range, IQR, is Q3 minus Q1. So you take the Q3 value you calculated and subtract Q1. So first you find the first quartile, then the third quartile, compute the range, you subtract them, compute the outlier boundaries. These boundaries are cutoff points to determine the outliers. The lower outlier boundary is Q1 minus 1/2 of IQR. The upper outlier boundary is Q3 plus 1.5 IQR. Any value data set that is lower than the boundary or greater than the upper outlier boundary is considered to be an outlier. So here we have our table represents student absent in middle school, and we want to know if there's any outliers. So they use the TI-84 to calculate the quartiles. For first quartile they got is 45, third quartile they got is 59. You get the IQR, so you subtract the two numbers and you get 14. To calculate the lower boundary, you do 1.5 times 14, and 1.5 times 14 is over here too, so you take 45, which is Q1, minus that, and you get 24, and then take 59, plus that, you get 80. So there are no values less than 24, but the value 100 is greater than the upper boundary. Therefore, the value